Now you know the essence of what transfer learning is, it's time to create your very own version of Teachable Machine. Let's get started. Head to the TensorFlow.js boilerplate page and fork a new copy that you'll use to implement this project. In this section, you'll be replacing the code in index.html. Go ahead and open that up and then replace with the code on the following slides. The only part of index.html you'll need to update is the content contained within the body tags as shown. First, you'll add a heading and a paragraph tag with ID of status. This is where you'll print the information to as you use different parts of the system to view outputs. Next, a video element with an ID of webcam is defined, to which you'll render your webcam later. Moving further down the code, you can now define some buttons. The first with ID of enable cam will simply enable the web camera. The buttons with class data collector will allow you to gather example images for your classes of data. The code you write later will be designed in such a way that you can add any number of these buttons and they'll work as intended automatically. Note that this also has a special user-defined attribute called data-1hot with an integer value starting from 0 for the first class. This is the numerical index you shall use to represent a certain class's data by, which will later be used in your 1hot encoding of the output classes. There's also a data-name attribute that contains the human-readable name you wish to use for this class. Next, you have a button to start the training with an ID of train, and a reset button with an ID of reset that will clear all of the data so you can start over. Finally, just like before, you have two script imports, one for TensorFlow.js and the other for your script.js that you'll define shortly. If you want to copy and paste the code directly, the completed index.html file is available at the URL shown. Next, you can replace content in style.css to add style to your HTML elements. Here, some styles are added to position and size elements correctly. Nothing too special. You could certainly add to this later to make an even better UX if you wanted to. Again, if you want to copy the styles directly, the URL provided has a complete version of style.css to save time. Now, assuming you copied the HTML and CSS correctly, the live preview will look something like this. Okay, so next is time to write the JavaScript code that will all be contained within script.js. Go ahead, open that up, and copy the code onto the following slides as you go along. First, start by adding some key constants that you'll use throughout the app to the start of your script.js. Let's walk through them. Status simply holds a reference to the paragraph tag that you'll write status updates to. Video holds a reference to the HTML video element that will render the webcam feed. Next, you can grab references to all the key buttons from the HTML page. First, you have a button to enable the camera, a reset button to reset the app to start over, and a train button to begin training after data is gathered for each class. You can now define the expected input width and height for the MobileNet model. The one you'll be using expects an input image of size 224 by 224 pixels in size. By storing this in a constant near the top of the file like this, if you decide to use a different version later, it makes it easier to update the values just once instead of having to replace it in many different places. Next, a constant called stopDataGather is defined and set to -1. By giving this number a more meaningful name like this, it will make the code more readable later when you use it. Essentially, this variable stores a state value so you know when the user has stopped clicking a button to gather data. Finally, you have a simple array lookup called class_names that holds the human-readable names for the possible class predictions. This will be populated later. Okay, so now you've got the references to the key elements, it's time to associate some event listeners to them. Next, you can add click event handlers to key buttons. First, the enable cam button. It will call the enable cam function when clicked. Second, the train button will then call the train and predict function when clicked. And finally, the reset button that will call reset when clicked. Finally, in this section, you can find all buttons that have a class of data collector using document.querySelectorAll. This will return an array of elements found from the document that match that class. You can then iterate through the found buttons and associate two event listeners to each, one for mouse down and one for mouse up. This allows you to keep recording samples as long as the button is pressed, until the mouse button is no longer pressed, which will be useful for data collection. Both events will call the gather data for class function that you'll define later. At this point, you can also push the found human-readable class names from the HTML button attribute data-name to the class names array. Now, by using a class to find the buttons here and not hard-coding a fixed number of data collector buttons, it allows you to change your HTML later to add more buttons, and the code will still function correctly for 3, 4, or any number of buttons like this. On the next line of code, you can add some variables to store key things that will be used later. Let's walk through those. First, there's a variable to store the loaded MobileNet model. Initially, this is set to undefined. Next, you have a variable called gatherDataState. If a data collector button is being pressed, this will change to be the one-hot ID of that button instead, as defined in the HTML. So that way, you know what class of data you're collecting in that moment. Initially, set it to the stop data gather value so that your data gather loop that you'll be writing later will not gather any data when no buttons are being pressed. Next, video playing allows you to keep track if the webcam stream is successfully loaded and playing such that you can actually use it. Initially, this is set to false as the webcam is not on until you press the Enable Cam button. Next, define two arrays, one for training data inputs and one for the outputs. These will store the gathered training data values as you click the data collector buttons. Now, one more array is now defined to keep track of how many examples are contained for each class once you start adding them. And finally, you have a variable called predict that will control your prediction loop. This is set to false initially. No predictions will take place until this is set to true later. Alright, so all the key variables have been defined. Let's go and load the pre-chopped up MobileNet v3 that will provide an image feature vector instead of classifications. First, define a new function called loadMobileNetFeatureModel as shown. This must be an async function as the act of loading a model is asynchronous. Next, you can define the URL that the model you want to load is located at from the TF Hub documentation. You can then actually load the model as you've done before using await tf.loadGraphModel, remembering to set the special property from TF Hub to be true as you're loading a model from this website. Remember, this is a special case only when using models hosted on TF Hub. Once the loading is complete, you can set the status elements in a text with a message so you can visually see it's loaded correctly and you're ready to start gathering data. The only thing left to do now is to warm up the model. With larger models like this, the first time you use a model, it can take a moment to set everything up. Therefore, it's wise to pass zeros through the model once before you start using it elsewhere to avoid any waiting in the future where timing might be more critical. As you've seen before, you can simply use tf.zeros with a batch size of 1 and a height and width of the correct size. And finally, the color channels, which in this case is 3 as the model expects RGB images. You can then log the resulting shape of a tensor returned using answer.shape to help you understand the size of the image features this model produces. Finally, you can immediately call this created function to get loading underway. If you view your live preview right now, after a few moments, you'll see the status text change from awaiting TF.js load to become MobileNet v3 loaded successfully as shown on this slide. Ensure this worked before continuing. You can also check the console output that would have printed the size of the output features that this model produces. After running zeros through the MobileNet model, you'll see the shape of 1024 printed. As the first item is just a batch, you can see that it returns 1024 features that can hopefully then be used to help you classify new objects. Okay, so now it's time to start defining your model head, which is essentially a very minimal multi-layer perceptron. Start by defining a tf.sequential model just like you've done before. Next, add a dense layer as the input layer to this model. You'll have an input shape of 1024 as the outputs from the MobileNet v3 features are of this size as you saw in the previous step after passing ones through the model. This layer will have 128 neurons that use the ReLU activation. Now you can add the output layer. Here, the number of neurons should equal the number of classes that you're trying to predict. To do that, you can use class_names.length to find how many classes that you're planning to classify. As this is a classification problem, you'll use the softmax activation on this output layer. Now print the model summary to the console to ensure everything is looking as expected. Finally, you can compile the model so it's ready to be trained. Here, the optimizer is set to Adam, and the loss will either be binary cross entropy if class_names.length is equal to 2, else it will use categorical cross entropy instead. Accuracy metrics are also requested so they can be monitored in the logs later on. At this point, if you check your console output, you'll see the following printed to your screen. Note that this has over 130,000 trainable parameters, but as this is a simple dense layer of regular neurons, it will train pretty fast, unlike the CNN model you previously made. Now you could try changing the number of neurons in the first layer to see how low you can make it while still getting good performance. I'll leave that as an activity for you to do once the project is complete. Alright, next you can create a function to check if the browser supports getUserMedia as you've seen before. Now you can flesh out the enableCam function. First check if getUserMedia is supported using the function you just defined above. If it isn't, you can print a warning to the console. And next, define some constraints for your getUserMedia call. This is just like you've done before, but in this case, you also specify you prefer the width of the video to be 640 and the height to be 480 pixels. But why? Well, there's not much point getting video larger than this, as it will need to be resized to 224 by 224 anyhow to be fed into the MobileNet model, so you may as well save some computing resources by requesting a smaller resolution. Most cameras support a resolution of this size. Then, just as you've seen before, you can call navigator.mediadevices.getUserMedia with the constraints above, and then wait for the stream to be returned, at which point you can get your video element to play the stream. And then add an event listener for the stream to load. In this case, once the stream loads, you can set video playing to be true and remove the Enable Cam button to prevent it from being clicked on again by setting its class to removed. Now, if you run your code at this point and click the Enable Camera button and allow access to the webcam if it's your first time using it on the site, you should then see yourself render to the video element on the page as shown. Okay, so now it's time to add a function to deal with the data collector button clicks. Okay, so first define a new function called gatherDataForClass as shown, which is what you assigned as your event handler function at the start of this lesson. Next, you can check the data-1hot attribute on the currently clicked button by using this.getAttribute with this attribute's name, in this case data-1hot as the parameter. As this is a string, you can use parseInt to cast it to an integer and assign this result to a variable called classNumber. Now you can set the gatherDataState accordingly. If the current gatherDataState is equal to stopDataGather, which you set to be -1, then that means you're not currently gathering any data and it was a mouse down event that fired. Therefore, you want to set the gatherDataState to be the class number you just found. Otherwise, it means that you're currently gathering data already and the event that fired must have been the mouse up event, meaning you want to stop gathering data for that class. So you can just set it back to the stopDataGather state, which will end the data gathering loop that you'll define shortly. Finally, you can kick off the dataGather loop that will actually perform the recording of class data. Naturally, now it's time to define the dataGather loop function. This function is responsible for sampling images from the webcam video, passing them through the MobileNet model, and capturing the outputs of that model, the 1024 feature vectors. It will then store them along with the gatherDataState ID of the button that's currently being pressed, so you know what class the data represents. Let's walk through it. So first off, you're only going to continue if video playing is true, meaning that the webcam is active and gatherDataState is not equal to stopDataGather, meaning a button for class data gathering is currently being pressed. Next, wrap your code in a tf.tidy to dispose of any created tensors in the following code efficiently. The result of this tf.tidy code execution will be stored in a variable called imageFeatures. Now you can grab a frame of the webcam using tf.browser.fromPixels as you've used before. The resulting tensor will be stored in a variable called videoFrameAsTensor. Next, you can resize the videoFrameAsTensor variable to be of the correct shape for MobileNet. Here you can use a tf.image.resizeByLinear as seen before with a tensor you want to reshape as the first parameter, and then a shape that defines the new height and width you require, which are defined by the constants you already created at the start of this lesson. Finally, set align corners to be true in the third parameter as you've done before. The result of this resize is stored in a variable called resizeTensorFrame. Now clearly, this will stretch the image as your webcam image is 640 by 480 pixels in size, and ImageNet needs a square image of 224 by 224 pixels. For the purpose of this demo, this should work fine. However, once you complete this lesson, you might want to try and crop a square image from this instead for even better results for any production system you might create. Now you must normalize the image data. As you know, the image data is always in the range of 0 to 255 when using tf.browser.from pixels. You can simply divide the resized tensor frame by 255 to get all values between 0 and 1. Finally, you can push this normalized tensor through MobileNet by calling mobilenet.predict, to which you pass the expanded version of the normalized tensor frame using expand dims, so it's a batch of 1 in a tensor 2D. Once this result comes back, you can then immediately call squeeze on that to squash it back down to a 1D tensor, which you then return and assign to image features that captures the result from tf-tidy. Now that you've got image features from MobileNet, you can record them by pushing them onto your training data inputs array that you previously defined. In a similar fashion, you can also record what this input represents in the training data outputs array by pushing the current gather data state to that array. Note that the gather data state variable would have been set to the class's current numerical ID that you're recording data for when the button was clicked in the previous gather data for class function that you defined. At this point, you can also increment the number of examples you have for a given class. To do this, first check if the index within the examples count array has been initialized before or not. If it's undefined, you can simply set it to 0 to initialize the counter for a given class's numerical ID. You can then simply increment the examples count for the current gather data state. Finally, you can update the status text on the web page to show the current counts for each class as they're captured. To do this, you can just loop through the class underscore names array and then print the human readable name combined with the data count at the same index in examples count. Last but not least, call window.requestAnimationFrame with data gather loop passed as a parameter to recursively call this function all over again. This will continue to sample frames from the video until the button mouse up is detected and gather data state becomes stop data gather, at which point this data gather loop will end. Okay, so if you run your code at this point, you should be able to click the Enable Webcam button, await the webcam to load, and then click and hold on each of the data gather buttons to gather example data for each class. You should see that the status text is updated accordingly as it starts to store all the tensors in memory as shown on this slide. Alright, so the next step is to implement your train and predict function, which is where the transfer learning actually takes place. First, ensure you stop any current predictions from taking place by setting predict to false. Next, shuffle your input and output arrays, just like you've done in the prior examples on this course. Now you can convert your outputs array to be a tensor 1D of type int32, so it's ready to be used in a one-hot encoding. This is stored in a variable named as outputs as tensor. You can then use the tf.oneHot function with its outputs as tensor variable along with the max number of classes to encode, which is simply the class underscore names.length. Your one-hot encoded outputs are now stored in a new tensor called oneHotOutputs. Now, currently, training data inputs is an array of tensors. In order to use these for training, you'll need to convert the array of tensors to become a regular 2D tensor. To do that, there's a neat function within the TensorFlow.js library called tf.stack, which, as you may have guessed, simply takes an array of tensors and stacks them together to produce a tensor as output instead. In this case, a tensor 2D is returned, which is what you need for training a batch of one-dimensional inputs that are each 1024 in length, containing the features recorded. Next, you can await model.fit as you've done in prior examples. Here, you can now pass your inputs as tensor variable along with the one-hot outputs. Set shuffle to true, use a batch size of 5 and 10 epochs, and of course specify a callback for onEpochEnd to log progress. Finally, in this function, you can dispose of the created tensors as the model is now trained. You can then set predict back to true to allow predictions to take place again, and call the predict loop function to start predicting live webcam images. Now, just below this function, you can also define the log progress function as you've done so before to log the state of training that's used in model.fit above. Alright, so you're almost there. It's time to add the predict loop function to make predictions. First, check that the predict is true, so the predictions are only made after a model is trained and is available to be used. Next, you can get the image features for the current image just like you did in the data gather loop function before. Essentially, you grab a frame from the webcam using tf.browser.fromPixels, normalize it, resize it to be 224 by 224, and then pass through the MobileNet model to get the image features. Now, however, you can use your newly trained model head to actually perform a prediction by passing the image features just found through your model.predict. You can then squeeze the resulting tensor to make it one-dimensional again and assign it to a variable called prediction. With this prediction, you can find the index that has the highest value using argmax as you've done in prior examples, and then convert this resulting tensor to an array form sequentially using arraysync. This value is stored in the variable called highestIndex. Next, you can get the actual prediction confidence scores in the same manner by calling arraysync on that tensor directly too. You now have everything you need to update the status text with the predictions. To get the human readable string for the class, you can just look up the highest index in the class_names array and then grab the confidence value from the prediction array in the same manner. To make it more readable, as a percentage, just multiply by 100 and math.floor the result. Finally, you can use window.requestAnimationFrame to call prediction loop all over again once ready to get real-time classification on your video stream. This will continue until predict is set to false if you choose to train a new model with new data. Which brings you to the final piece of the puzzle, implementing a reset button. First, stop any running prediction loops by setting predict to false. Next, you can delete all the contents in the example's count array by using the splice 0 trick you learned before. Now go through all the current recorded training data inputs and ensure you dispose of each tensor contained within it to free up memory once again. Now that the tensors are destroyed, you can now safely call splice 0 on both the training data inputs and the training data outputs arrays to clear those too. Note that if you had called splice 0 on the training data inputs array before disposing the tensors would be unreachable but still be in memory and not disposed of, which would be very, very bad. Finally, set the status text to something sensible and print out the tensors left in memory as a sanity check. It should be noted that there will be a few hundred tensors still in memory, as the MobileNet model and the multi-layer perceptron that you defined are not disposed of, as you might want to reuse them with new training data if you decide to train again with a new dataset after this reset. Alright, it's now time to test out your very own version of Teachable Machine. Head to the live preview, enable the webcam, and gather at least 30 examples for class 1 for some object in your room, and then do the same for class 2 for a different object. Hit train and check the console log to see the progress. Now it should train pretty fast, and once trained, show the objects to the camera to get live predictions that will be printed to the status text area on the web page. If you're having trouble, check my completed working code on the link shown to see if you missed copying anything over. So congratulations! You've just completed your very first transfer learning example, and you've just gone full circle and implemented the amazing things you saw at the very start of this course. This is huge progress and should take a very well-deserved coffee break at this point. Of course, you can make this demo much more elaborate with a much nicer UX and interface if you wish, but that's all just regular web engineering that you already know about. Think about how you could use this in your future client work. Maybe you could recognize the client's products and trigger a video to play when they're found to provide users with useful information about them. The possibilities are endless. Now, in the next section, you'll see how to use the layers-based models to do the same thing in a slightly more useful way. Right now, if you want to use the resulting trained model that you made, you'll need to load two models. First, the MobileNet base model, used to generate the feature vectors, and then secondly, the trained multi-layer perceptron that you just trained. Now, this is not the end of the world, but it'd be nicer to download just one model to be slightly more efficient. If the base model was in fact a layers model, you could combine them after training is complete to then just save one model as an output. So see you in the next section to see how to do that.